So good morning, my dear friends.
Good morning, sir.
Today we will conclude the planar failure mode. In the last class, I have tried to show you the theoretical development take place for the analysis of planar mode of failure. And in that context, we have learned the influence of different parameters, external parameters, external factors. That is the groundwater regime, four kind of groundwater regime we have studied and we have analyzed. Similarly, we have tried to connect our analysis with the critical locations and critical length of the cracks. So it is a very difficult process to physically characterize these geological features. Now today we are specifically focus on special topic of planar failure. Why it is special? It is special in the sense we have laid down five principles, five conditions. Based on that, we have categorized it is a planar mode of failure. When in totality, this aspect predominantly will be satisfied, but some point will be violated. And we cannot categorize this kind of failure as another category of failure. So that is basically a special topic in the planar mode of failure. If you could remember, in the first slide we have shown you a picture, a bedded deposit. Bedded deposit was parallelly oriented to the slope face. And in that bedded deposit, the weakness plane is parallelly oriented to the slope face. So the weakness plane psi p was not less than the psi f. Suppose what will happen? This is a kind of one experiment you see in a construction wall. Construction wall. Sometimes what happens if there is a plaster in a wall, there is a plaster. Plaster is basically a upper layer of the wall. So due to some majorly chemical process, due to that, what happens? A gap is created between the wall and the plaster. Okay. So at that particular position, we observe a chunk of plaster is dislodged from the wall. Dislodged from the wall. And if you hammer it, you can notice that there are some sound from an intact plaster and wall. Sound is different. It is the role of the air. By this, I want to mean the plaster is basically an outer layer of the wall. And if you consider the total plaster as a continuous layer, so this continuous layer is aligned parallel to the wall. So if a weakness is created in the bottom of the plaster, what will happen? a tension will be generated in the top portion of the plaster. Tension will be generated in the top portion of the plaster. This is a physical reality we all observe in our day-to-day domestic life. Same thing, if we extend this concept to the rock slope, if the sheet of rock that is parallelly oriented to the rock slope, and this is a very thin, so in that case, what will happen? So due to the weakness in this particular bottom layer, the top portion will try to give some amount of force on that particular sheet. So sheet is basically thin. So if a rod is applied, a thin rod is applied, a rod is going to be buckled. This is another property of a general material, metal, iron, steel, like that. It is not the property of the rock. But for a thin section, this kind of property can also be compared, the like the buckling property of a metal. So this is what I want to mean. So if this kind of very fine sheet is aligned in the parallel to the slope, and if there is a redistribution of the force of the forces occurred, so it is going to be bulge. It is going to be bulge at the bottom. So this bulging is not equal all along the plane. This bulging is not equal all along the plane. So based on that, we will separate out one by one. This is one zone, this is another zone, this is another zone. So these are the things we will study today. The second most important thing we will study today is about the remedial measures. We have already studied how the failure will occur, how we can estimate the failure, how we can calculate the amount of stress developed at different point of time in the slope, but how to mitigate, how to address, how to rearrange using some artificial measures. So that is basically the remedial measures we will try to study. So by that we will complete the portion that is required for a plane failure analysis model. So this is what today we will discuss. So let's start today's discussion. Now it is visible. Presentation is visible.
Yes, sir.
So today we will try to study a deep slope stability, and this deep slope stability I want to mean that is not daylighting in the slope phase. That is not daylighting in the slope phase. So that is a special kind of slope. This is the special kind of slope we will focus today. If you try to concentrate on these figures, the first one, this is a sheet, a very thin sheet associated with this rock mass. But the property characteristics of the thin sheet is separate from the rock mass. Now, if some amount of stress is developed, not only some amount of stress, due to the self weight of this thin layer at the bottom, there is a tendency to buckle. This is same is applied for any kind of material. So if this buckle is observed, so what will happen here? Here there will be a development of tension crack, because in this particular position, material is trying tearing it out from reverse direction, in opposite direction. So due to that, in this particular juncture, a tension will develop. A tension will develop. And if the tension will develop, we know rock is not in a position to resist that tension. Even the small amount of tension, it is very difficult for the rock to resist. So what will be the manifestation? Manifestation is the crack or failure. Okay. So this is a second one. Second one, after the stage one, crack will develop, and the development of the crack, it will be segregated into two separate slabs. It will be segregated to separate two slabs. Another thing may happen. Another thing may happen, that is a third quality. That is a third quality. What is the third quality? Now, if by chance there is some deflection, there is some deflection in the seat, and due to the deflection, the seat, due to the this is a long slope, height maybe 20 meter, 15 meter like that. This is a special kind of slope. So due to the sail point, that will try to pressurize the bottom one, and due to this pressurization, the bottom seat will try to be dislodged like that. Dislodged like that, and finally what will happen, this kind of thing, there will be a huge amount of movement will be occurred in the bottom. Huge amount of movement will be occurred in the bottom. Not only that, top portion will be slided along the slope face. Top portion may be slided along this weakness plane, that is a bedding plane. So this kind of slope does not daylighting the slope face. The number one consideration in our planar mode of failure, it is not satisfied in that sense, but other thing more or less satisfied, because plane failure is along a planar one, and that is also striking parallel to the slope face, and also there is a visible discontinuity plane through which this failure is occurring, and rest of the parameter more or less satisfied. So this kind of failure have to be addressed by our development of the idea of the planar mode of failure. So let's see how we can analyze our cases. Now, based on this concept, we have tried to develop a concept of biplanar deep slope. Biplanar deep slope. This biplanar deep slope is basically showing a rock failure transition from one stage to another stage. Okay, this is what the biplanar. Here, it is a stage 1, it is stage 2, it is stage 3. The stage 1 basically the biplanar instability of the steep slope with down slope movement relatively of the thin active slab. Okay. Second is basically the rock fracture. Here, due to this upthrust pressure, pressure from the top to bottom, this portion you have a tendency to develop a block or grain. Okay, because this will be compressed. So at that position, the rock will be broken, okay, into a different small wedge. Okay. And the third is this portion. This is the third one. This portion will try to move away to the toe, and that actually release the overall pressure developed on this particular portion. So it is understood now. In the top portion, it will exhibit a relative motion, and due to this relative motion, finally what will happen? Relative motion means what? Relative motion means some work done. Work is basically force into displacement. So if some work is done in this slab, this work may be done by this what? Self weight, that is a force. and the amount of displacement, if it is multiplied, then that is a work, and if that work is done, an energy will be produced, and due to that energy, finally this portion will be broken down, and the third portion have a tendency to slide it out, move out of the tool. So this is a kind of situation will arise in a biplanar mode of. The same thing been studied by McLoughlin and Doolin in 2005. They have published their work using some method called DDA, discrete element analysis. Okay, so this is this was a earlier concept of discrete element method, DEM. So before the advent of DEM, DDA was developed in the 1988 by C et al. C et al. Have done some research on that and his PhD work on that. So he developed this DDA method for analysis of the block interaction in a rock mass. Okay, so that was very successful study. So McLoughlin and Doolin, 2005, they have used this DDA method. This DDA method toolbox is freely available. It is open source software. You can use it. So they have used it and they have finally concluded how this deformation, how this transition is going to be occurred, and it is basically the same that we have studied. Here, this portion will be broken down to a small size of wedge, and that is what it has been shown in this study. Now, the first thing that I have told you, that here there is a tendency of the buckling. Tendency of the buckling. The first case, it is a reality, because if this is a thin one and the pressure is applied, buckling is the only alternative. So this is for a particularly thin slab. This is for a thin slab, and when the ratio of the length and the thickness is around 1%, around 1%, this kind of situation will occur. Means height, if it is 20 meter, 100 of it is 20 meter, 100 of it what? 0.2 meter, 0.2 meter, 0.2 meter if it is, means 20 centimeter slab thickness and the height is 20 meter. On that kind of slope, a buckling will be a reality. And this has been shown by Kevers 1981. They have shown using their case studies, and this buckling will actually a reality in this kind of area. So here we can utilize the limit equilibrium concept that we have developed in the first part of the planar mode of failure and can be applied here, and based on that we can calculate the force developed and what will be the factor of safety. The second one, 3-hinge buckling. Okay, 3-hinge buckling. If you see the earlier picture, this is the B picture. Zone 1, zone 2, zone 3. So here they have that is Kala et al. Kala is a very much expert in the slope stability. They have developed this study in 2014. This is a very recent study, and they developed this is a reality for a orthogonal joint set. Okay, orthogonal joint set. Okay. This is a reality for a orthogonal joint set where joint is oriented perpendicular to each other. Okay. So here only, due to that, buckling can occur that will provide a lateral force. Okay, that will actually generate due to the water pressure present in the slope. So this process can also be studied. Instability can also be studied using the limit equilibrium method that we have already developed. And the last one of the figure first is basically here British Columbia a study been done in 2019, And they shown in the British Columbia mine that this kind of failure is a reality in a coal mine. Okay, coal mine, and this is a very complex. This is a very complex, and that is very difficult to be accommodated in limit equilibrium method. That is very difficult to be accommodated, and that can only be studied using numerical methods. That can only be studied using the numerical methods. So bending, then shearing, and everything. These are the things that is not possible to be accommodated in limit equilibrium method. That is why they have studied it separately, and they have shown for this kind of slope failure, this is LEM is not perform well, and it is not possible also to accommodate so many parameters. And in the biplanar instability that I have shown you the figure, okay, that figure is basically the top portion is the most active zone. Top portion is the most active zone because it is a free one that is going to exert pressure on the bottom one. Okay, okay. So the bottom one basically the passive lower passive zone. So that is basically taking the pressure from the top, and based on that it is basically transferring the pressure. There will be intermediate zone. Okay, there will be intermediate zone, and finally here the rock will fracture. Rock will fracture due to that pressure. Okay, so that is been modeled. That is been modeled by McLuhan and Dulin 2005. So they have shown that how block size will be for a given slope. This is basically how much? It is 200 meter. So it is 200, 400. It is around 600 meter. They have studied for a landslide condition of a hilly area. So around 600 meter height you can consider. So for a large rock mass movement in a landslide, they have studied and they have successfully predicted this kind of mechanism. Now, if we go into details of it, in a biplanar mode of instability, you see this is the active zone. This is the top portion of the active zone because this is exerting pressure. This is exerting pressure on the bottom one. Okay, this is the transition zone because this portion is all are in an intact position, but this is intact in this from this layer, from this link, but it is exerting pressure. So finally this portion is under strain condition. This portion is under strain condition. So if it is under strain condition, at some point of time it will break, it will fail. That the material is failed in triaxial test we have observed along a shear plane. So failure will occur, and the rock will break into a small fragment. So this is a transition zone because this transition zone is actively experiencing the pressure from this active zone. The last one is the toe release surface. So because finally if the failure is occurred, so all force is redistributed because the force is released. So this is basically a passive zone. Okay, and here only the manifestation of the movement is observed. So this kind of things get accelerated due to the development of water pressure. If water table is intersecting this kind of plane, we have already told you that we are assuming flow through the rock is negligible. So we are only assuming flow through the weakness plane. So according to weakness plane have a different geometry. Based on that, they have developed the triangular force diagram of the water pressure, and that pressure will exert pressure in this direction, and that will accelerate finally the slope towards failure. Now, this biplanar mode of instability can be studied using the Moore-Coulomb failure hypothesis. And using the molecular failure hypothesis, they have come out with this relationship psi p is equal to psi s plus phi divided by 2 minus 45. This is basically coming from this figure. This is coming from this psi s is the angle of the slope surface or slope face here, and psi p is the weakness plane angle. Here is the weakness plane angle, and phi is the slope friction angle, and this is the theta, this is beta. Based on that, we can found out the value of theta and beta. So this is basically the development based on the limit equilibrium concept. So this is been developed by Hapage, State, Eberhard et al. 2014. This team is also from University of British Columbia. They have studied in details this kind of failure, and they have come out with a conclusion of this relationship. So this is basically what from this particular angle, it is a measurable quantity. We can measure it, but we cannot measure theta and beta. So theta and beta can be come out using this formula. Theta and beta can be come out using this formula. Friction angle of the material is known. Theta can be found out, and if theta is found out, beta can also be found out. Okay, and if it is known, psi s, psi p can also be found out. So these are the things. These are the interconnected and coherence concept of the failure in planar mode of failure. Now, let us concentrate on the remedial measures for the deep slope. How we can avert a sure shot failure so that a failure is averted and finally slope is in a stable condition. The majority of the geoscientists have focused the requirement of drainage, and this drainage to be drilled in such a way, the drills should be in such a way that will be able, that will basically that will able most effectively to depressurize the zone. Okay, along with that, flow will occur. So we have to ensure, we have to align the drill hole in such a way, drainage in such a way that water gets a path to travel to expose to the atmospheric pressure, because it is in a high pressure zone and it is in a low pressure zone, so water will automatically come out if the sufficient drain arrangement is there. Along with that, they are focusing that due to this drain, this will effectively channelize the depressurization in the slope. So in that sense, drainage will going to help us for the enhancement of the slope stability by reducing the active stress. Second option is a toe buttress. This buttress concept is nothing but a kind of things. Something is moving, so what we do? Some thrust force to be given. So thrust force is, if it is to be given, if it is a larger one, a larger amount of thrust force should be given, so that effectively we can arrest the movement. So this toe buttress concept is very in limited use in the mine, because that actually need a large amount of space. In a open pit mine, if large amount of space is occupied in a bench, so the road will be get stuck. So the movement, the work will be affected. So toe buttress is not an effective concept, but sometimes, whenever it is possible, we are going for a toe buttress because it is most easy. If the material density is 17 kilonewton, so we are placing those bulky amount of material whose density is more. If the density is more, that will exert a higher amount of pressure on that wall, and by that higher amount of exerting on the pressure, effectively what will happen? Effectively, it will happen to be in a stable condition. Not only so, in a condition where the groundwater flow is a reality, this bulk amount of material will also help to drain out the water easily through those bulk material. So it will not stuck. It will not stuck the water to be stayed in the slope phase. So it will actually help the water to come out of the wall through this buttons. Third option, third method that is followed. Uh, this is widely followed in different mines, or that is called rock bolting. Rock bolting. This bolting may be of tensioned rock bolt or maybe untensioned, whatever it may be, based on the requirement. But whether it is to be fully grout or half grout, that is also to be decided based on the condition. But a very important concept to be remembered here. It is not here. Important concept is when a series of bolt to be installed in a rock face. Now I should use the board. That would be better. So my screen is visible. So the concept is in 3D. Suppose this is a top view. It is a top view. Okay. So we are inserting series of rock bolts. Series of rock bolts. This is I am observing from the top of the mine. Okay. So this portion actually not visible, but due to the clarity I am showing. So if this is the kind of rock bolt is installed in a mine, in a rock slope, what is the limitation? Can anybody say? What the problem will arise for this kind of slope? Anybody can predict?
Can you please repeat the question? Can you please repeat the
Is it
question?
visible this screen? This is a rock bolt. If I align the rock bolt in such a way, this is a top view rock bolt. What is the problem of installing rock bolt in such a fashion? If all rock bolt length is equal, all rock bolt length is equal L, and L length rock bolt is used uniformly in the slope face, what problem will arise? Rather than we will use L1 length, L2 length, L3 length like this. This is another phase. First bolt is this, second bolt is this, third bolt is this, fourth bolt is this, fifth bolt may be like this, like that. So all length are not equal to each other. What is the difference? This is a first case, this is a second case. We should not follow the case 1. Why? Anybody can give light on this particular question? Ashish?
I think
Ashish,
shear failure. Yes, sir. I think shear failure will happen.
where the shear failure will occur? This is a slope face.
Because
We are installing bolt in such a way. This is a single bolt I am showing you. This is a single bolt. This is a single bolt. I am telling the length of this bolt L1 should not be equal to L2, should not be equal to L3. Rather, it may be long, it may be small like that, or it may be like that. Why? Because if it is uniform, if it
The
is
planar failure will not attach to every
no,
bolts.
no, 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 no. Plane of failure, the intact portion is already attached here. But what will happen? What will happen? What will happen? Oh, oh, delete that. The new one. To cut. Oh, okay, left it. Actually, what will happen? That if all length is equal, due to this all length are equal, along this line a new crack will develop. Along this line new crack will develop. That is why we always follow all the bolt length should not be equal. Okay, because due to this one a discontinuity, a weakness will occur, and finally it may be extended each other and will be joined, and finally this will be a weak zone. So to prevent that, we are using a different length of the bolt so that this kind of situation does not arise. It is understood now? It is understood now?
Yes.
Ansi? It is understood?
Yes, sir.
So because we are going to avoid a further deterioration in the slope phase, because this kind of orientation of the rock bolt, if it is installed, that actually developed a new weakness plane that we should not allow to occur. Okay, so the rock bolt is another solution, and the fourth is the unloading is another solution. This unloading is very difficult. So based on the blasting conditions you have assumed in the mines. So time based on the particular characteristics, we have to select whether this unloading is possible in the particular case, or unloading by means of reducing the water pressure. Whatever it may be the possibility, we can go through that, because these are the things that is easier to handle. The last one, if nothing can be done, we will keep some distance from the slope, and we will not allow any movement within that limit, within that length. So that basically the method we follow in mines, okay, in a slope stability cases. Now, if we install a rock bolt, what will happen? Let's see the picture first, then I will analyze. Now, if I install a rock bolt, what kind of differentiation of the stress distribution is occurring? Think about this scenario. This is filled with water, so it will exert U amount of pressure, V amount of pressure this direction, U amount of pressure this direction. Both are going to reduce the effective normal pressure and subsequently also increasing the mobilizing shear. But by the installation of the rock bolt, due to the installation of the rock bolt, I am increasing the effective normal pressure. If I increasing the effective normal pressure amount, so the resisting shear will be get reduced. Side by side, due to this attachment, stitching of these different block, stitching of the different block, the horizontal movement, horizontal force, that is parallel force developed on the weakness plane, is also get reduced by substantial amount due to the installation of the rock bolt. So it will increase the effective normal pressure. Side by side, it will decrease the amount of parallel force acting through the weakness plane towards mobilization of the block. So if this is true, then our factor of safety expression will be like this: CA cohesion will not be altered, W cos psi p minus U minus V, that was initial one, due to the presence of water. Now this is enhanced, T sin psi t psi p multiplied by tan phi. This was the initial one due to the presence of water. Now this shearing amount is also get reduced, T cos psi t psi p. Okay. Now if it is so, then there is a limitation that psi p and psi t is less than 90 degree, because we can install in this direction or install in this direction, whatever maybe the advantage one, that we will follow time to time. Based on that concept, it is observed that optimal installation angle of the bolt is basically an optimal amount of performance of the bolt will be achieved only and only if the installation angle is like this: psi t optimal is equal to phi minus W psi p. So if the friction angle of the material is 27 degree and psi p angle is 12 degree, so 27 minus 12 is 15 degrees, the effective installation of the bolt. Okay, so based on that, we will follow the installation of the bolting pattern in the rock slope. Now, if we extend this concept, now we will install a series of rock bolt. And we have already understood there's a T component. T component is basically a tensioned rock bolt. So tension is applied. So amount of tension is applied on the rock bolt, and if it is so, how many number of bolts to be installed? And what would be the spacing? What would be the spacing of the rock bolt? Based on that relationship, we have developed this relationship is equal to spacing. So optimal spacing will be TBN. So TB is basically the tension bolt quantity, the amount of tension bolt quantity, and n number of bolt is installed. And if it is the T is the required bolting force is required, total required force is required. So S can be found out easily, TB into N divided by T. So based on this relationship, we design the amount of bolting required in a rock slope. There are also options for reinforcement with fully grouted untensioned joint. It is not a tensioned one. Okay. So in this case, we observe it is going through 3 stages. Okay. One is the elastic stage. So elastic stage is basically after overcoming the cohesion of the joint, okay, the block will begins to slide. And it will slide along each other. And due to that, a shear resistance of the dowel will actually will help the rock to be in that position. That is the elastic stage. Second is the yielding stage. So after some point of time, it is basically up to that limit it can only offer the resistance. Up to that limit it will only offer the resistance, and rest, if it is not able to do that, it will reach the plastic stage. So plastic stage is not expected as per design, but in the long run it is always a reality. So we have also considered this stage, the plastic one. So this is a kind of installation of the dowels. Is followed in the field. This has been taken from the Spang and Egger 1990 work. So they have shown how to install this kind of dowels. And the last is the reinforcement by the buttress. The buttress is basically accumulating a large amount of material on the toe of the rock slope. By placing this kind of material, this material is going to exert a horizontal thrust force, and this horizontal thrust force will act as a arresting force, and this arresting force is going to help that this slope is not going to be mobilized or sheared or move along this plane. So up to certain limit, this kind of buttress wall is effective. And sometimes what happen, a concrete buttress wall is also erected in a civil cases, in a different embankments in military purpose, whatever there. They have erected a they erect a wall, okay, made of reinforced concrete. So that wall basically is giving a horizontal thrust force on the slope, and slope will remain stable. And they have designed this wall in such a way that wall is going to accommodate that amount of pressure developed on the slope, and the shear force developed on the slope, that it will accommodate, and slope will remain stable at this position. So this is all about the special kind of planar failure mode and its associated concept and the remedial measures to be adjusted in the field so that we can avert possible mode of failure. This is all. Now I request my dear friends to raise your hand so that one by one I can question your answer and clear the doubt. Ajay,
Yes, sir, it is clear, sir.
Ashish,
Sir, I have a doubt.
tell me.
Sir, why we comparing this rock slope with sir, why we comparing rock with a reinforcement?
Why?
In the starting, we learning that a rock slope has failed about buckling,
Buckling, yes, buckling, yes.
but buckling properties having in the material to the having tensile strength, na sir.
Now, can you precisely place your question? What is your question?
My question is, rock is, I think, brittle material. Rock is having property for brittleness,
Okay,
and and reinforcement is property having ductile.
okay. Now proceed.
So why we comparing these two? Both. In some case, rock is rock showing some properties having similar to ductile.
I have not shown I have not uttered a word ductility. I have uttered the buckling of the material. Okay. Buckling is a phenomena. Buckling property I have not discussed. Buckling is a phenomena when the thickness of this rod is very, very small compared to the length. What will happen? This is called buckling. This is a phenomena. Okay. I have tried to get familiarized with this concept that is a physical reality, and if the thin rock layer is very thin in a deep slope and that is separated by a weakness plane, and due to the self-weight material have a property to buckle. That is the things I have explained. That is not a buckling property. That is why when there is a kind of buckling kind of phenomena is going to develop, a tension will develop, and rock is not in a position to
To resist tension.
resist tension. So failure will occur and break will be there, and that is the things I have shown you. Is it clear?
Yes.
Haritharun? Yes, sir. Mansi?
It's clear, sir.
Okay. Natabar?
16 slide. 16 slide.
Huh?
16th slide.
16. 16. Window 16. Okay. Tell me. Setback distance. Tell me. Whatever.
सर पेंट डायग्राम कर सकते हो इसे?
Huh? Can you
सर डायग्राम
diagram? Which diagram?
for this.
Oh, this is a diagram. Okay. Now I will draw you this diagram for you. Okay, if you want. Let me give you this opportunity. Okay. The diagram will be like this. A new one. Suppose this is a slope. Okay. And we have observed a failure will be occurred, and based on the calculation we have predicted that 15-meter displacement is the maximum one. Okay. So in this 15-meter I will erect a marker. So it is a road. So I will not allow anybody to enter in this zone, or I will not allow active work to be conducted in this zone. So this is a distance. So this distance is marked for keeping a safe distance for the failure to be accommodated in the meantime and work to be continued in this side, like that. Now is it clear? Not over?
Barrier to not enter
Huh?
in this side.
Huh?
It is like a barrier to don't enter in this
Yeah,
side.
yes. This is I am marking the minors.
Yes, sir,
Minors
it's
should
clear.
not enter in this zone. Yes, you are right. Any more question, not over?
Okay, sir, it's clear.
Okay, Sanjeev.
No, sir.
Clear, sir.
So thank you. So tomorrow we don't have. On Tuesday again we will meet. And I have uploaded the format for the project. So please try
Sir.
to